in this section, we want to talk about optimizing functions with multiple independent variables, where in this case we're going to be applying a constraint. So a constraint is just going to be some limitation on the independent variables in our function. So in example 1, we're given the function f of xy equals 2xy. That's the function that we want to maximize. So another word to refer to that is to call it the objective function. So the function that we're interested in either maximizing or minimizing is the objective function, because our objective is to optimize that function. And then we're given some other restraint or some other statement, which in this case, subject to x plus y equals 18. So this is our constraint function. So we're applying a constraint that whatever x and y are, these two variables have to sum to exactly 18. So we're placing some limitation or some restriction on those two independent variables. Before we look at how we actually optimize this function, we want to introduce a new variable, which is the Greek letter lambda. So when we start throwing in Greek letters, that has the tendency to throw some people off. But the important thing to keep in mind is that lambda is just a letter. It's not any different than x or y or using a, b, or c until we give it some specific meaning or context. So in this case, this Greek letter lambda that we're going to introduce is going to be referred to as a Lagrange multiplier. Which really essentially just means that it's a new variable that we're going to introduce. And once we've introduced it, we'll look at trying to solve for it. So similar to how in the past we solved for x and y, lambda is just a new variable. We're going to be able to take partial derivatives with respect to that variable and apply similar techniques we've used in the past. So now that we have this idea of lambda, this Lagrange multiplier, we want to talk about our process for optimizing these types of problems. So the first thing we want to do is think about our problem and expressing it as the function we want to maximize, or in a minimization problem, the function that we want to minimize. So we want to maximize or minimize some function z equals f of xy. So that's that given objective function. And we want to identify our constraint function, which will be something of the form g of xy equal to 0. Now, when we look back at example 1, our constraint function isn't set equal to 0. So the first thing that we would do to start off this problem would be to set this function equal to 0 by subtracting the 18 from both sides. So in this case, our constraint function would be x plus y equals 18. That would be our expression g of xy. So once we've identified those two functions, we'll construct a new function, capital F of x, y, lambda. So we're going to introduce this new variable, and we're going to construct this specific expression, which will be f of xy, so whatever that original objective function is, plus this new variable lambda times our constraint function. So we identify the objective function, the constraint, and then we form this new function. Then we find any critical points of f, which means we want to solve the system. Capital F sub x, so the first derivative with respect to x, set equal to 0. F sub y, first partial derivative with respect to y, set equal to 0. So we'll take the first derivative with respect to x, with respect to y, and then also with respect to lambda. Set that equal to 0, and this will give us a system of equations to solve to get specific values for x, y, and lambda. If we end up with one critical point, so one coordinate pair x, y, lambda, or x naught, y naught, z naught, I should say. So we'll find a particular value for x, a particular value for y. Plugging those into the original objective function will give us some z coordinate. Then we can assume that x naught, y naught, whatever values we found for x and y by solving this system, is our solution. If we end up with multiple critical values, then we're going to evaluate our original objective function at each of those points that we found, and we'll say that the largest function value is our maximum, and the smallest is our minimum. So again, a few steps here where we identify the objective function, take the constraint and set it equal to 0 to generate this function g of xy. We establish this new function, capital F, which always has this particular form. Take the derivative with respect to each of those three variables, set those equal to 0 and solve that system, and that will generate one or more points, which we then identify as our solution, or evaluate the function at a few different points to determine whether we have maximums or minimums.